Good morning. Today we will introduce with the geometric ways of describing the crystal structure or crystal, the very important method, the method of crystallographic indexing. Here you can see the imagination of crystal lattice, the space crystal lattice, and I hope you remember the unit cell and the passport of unit cell metric, the set of angles alpha, beta, gamma, and the translation ABC. The method of crystallographic indication allows to determine any point, direction, plane in a crystal or crystalline structure independently of the coordinate system. To describe the crystal polyhedron, there is used the method of crystallograph indexing that is convenient for any crystallograph coordinate system, oblique or rectangular. Let's get acquainted with this method. Here, for example, the unit with the symbol 1 minus 2 minus 0, the first place coordinate x, the second place coordinate y, and the third place the coordinate z. The coordinate z in this case is absent. This unit, for example, minus x1 and 1, 2 minus y. Here you can see 1 minus, 2 minus, and 0. This set is the symbol of this unit. Let's go further. The direction is defined by 2 points, the beginning of coordinates and any point belonging to this direction. The symbol of this point is taken as a symbol of the direction and it's written in square brackets m and p and only integers. A series or a unit line as a crystal rib is characterized by the slope in the selected coordinate system. If the series doesn't pass through the origin of coordinates, we mentally move it so that it passes through the origin of coordinates. Thus, the direction of the series is defined by 2 points. The origin of coordinates and any unit of the series. Maybe this, maybe this. The symbol of this unit is taken as a symbol of the series and is written in square brackets, m and p, only integers. Obviously, this symbol describes a family of parallel series and parallel ribs of a polyhedron. Here you can see the crystallographic indices of the cube. The origin of coordinate system, the symbol of this point 0, 0, 0. For example, this unit, the symbol of this unit is 1, 0, 0. The symbol of this unit 1, 1, 0, 1, 1, and on to the coordinate of z is 0, and etc. And here you can see the directions, the symbols of directions of the cube. For example, here this the coordinate x of z 0, 0, 0, 0, 0, 1. The symbol of direction o y 0, 0, 0, 1, 0, and the axis of x 1, 0, 0, and etc. A series, for example, of 1, 1, 0 can be characterized as 2, 2, 0, and 3, 3, 0, etc. But to determine a symbol of this series, it is accepted to select a unit that is the closest to the origin. Crystal edges are intersected by parallel. You can see uh, the advantage of crystallographic indexing. Symbol of axis doesn't depend on the angles between the coordinate axis and the axial segments. Planar grids in the space lattice and the corresponding faces of the polyhedron are also characterized by a slope in the given coordinate system. Each crystal face is parallel to the planar grid, an infinite number of planar grids parallel to it. And further we set planes will be 2, 3, 0. A symbol HKL is characterized by the entire set of parallel planes. This symbol means that the system of parallel planes intercepts a segment in H paths, B in K paths, C in L paths, that is, cuts of segments are divided H, B divided K, C divided L on the coordinate axis. The symbol of the plane can only be an integer, positive and negative. But in radiography or X-ray analysis, the following entry was made this parenthesis, not here but this. Here you can see the crystallographic planes in the cube. For example, the plane 0, O, Y has the symbol. This plane is parallel the front of face, and the symbol of this set planes 1, 0, 0. This plane Z, 0, X has the symbol 0, 1, 0, and the plane X, O, Y are the same this plane, because this plane is parallel to this plane, has symbol 0, 0, 1. And here you can see the rest planes in the cube. For example, this plane, the symbol of this plane is 1, 1, 1. You can see 1, 1 and 1. This figure shows that if the plane is parallel to the axis of coordinates, that is intersects and at infinity, the index of the plane of this axis will be 1 divided by infinity is equal 0, as I say above. Thus, the symbols of the coordinate planes, regardless of the angles between the axes, will be always x, o, y, as I say, 0, x, o, y, 0, 1, y, o, z, 1, 0, 0, and x, o, z, 0, 1, 0. The method of crystallographic indexing had been established long before crystal lattice structures was proved by Max Lauer in 1912. It was based on a remarkable empirical law of crystallography called the law of integers. That means that plane A, H, B, H, C, H may be the face of a crystal only if a specified ratio is true. That is why the growing crystal have faces only of certain inclination, typical for substances. The faces for which the ratio PQR is irrational are impossible. As a rule, the PQR for these numbers don't exceed 5 for the real crystal. According to the Hayes law, the slope of every face of a crystal can be determined by three integers if the directions of the edges of the crystal are chosen as a coordinate axis, and for options as intercepts of one of the faces on this axis. Thus, any plane of face of a crystal can be determined by three integers. Millre's indices HKL that represent a value proportional to the inverse ratio of axial segments according to the law of integers. In order to find the Millre's indices, we should the first, to express segments intercepted by the plane of the axis in terms of A, B, C. The second, to find the inverse values of these quantities. The third, to bring the lowest possible rational indices to a common denominator. And the fourth, to discard the common denominator and obtain integers enclosed in parentheses. Then those tasks to make a plane HKL. In order to make a plane HKL, we should the first to put n on the axis segments A derived by H, B derived by K, C derived by L, and the second to put the obtained points on the plane of the family HKL, that is the closest to the origin. Symbols of planes and directions are determined by X-ray, although this can be done easily with the help of crystallography and projections. In conclusion of our lecture, I want to tell once more that this method is remarkable because symbols of axis and consequently the planes, points, the directions doesn't depend on the angle between the coordinate axes, and so this method is possible to use for any coordinate system, oblique or rectangular. And the end of our lecture, I want to show you a short video about this method. Thank you for your attention.